Hey everyone, in this AP Chem series video, I'll explain why sometimes there's extremely large increases in successive ionization energy values. First, remember that successive ionization energies are the energies required to remove one electron after another from the same atom, like we're showing here with these three subsequent equations. The first electron is the easiest to remove, so our first ionization energies will have the lowest values. And since the atom gets more and more positive each time you pull an electron off, it gets harder and harder to remove additional electrons after that. So on this list, the third ionization energy would be the highest because it's the most difficult to remove that electron. In this video, we'll get to see that an increase in ionization energy like we just talked about is always observed as more electrons are removed, but sometimes that increase is extremely large, and we have to be able to explain that too. Magnesium is a good example of this with the first, second, and third ionization energies shown here. So notice to remove the second electron only takes about twice as much energy as it did to remove the first. So it increases, but not by that much. The third electron, however, takes about 5 times as much energy as the second, and that is an extremely large increase. We're simply asking the question, why does that large increase exist? So to understand this, let's focus first on the first electron removal and the first ionization energy. We'll do that by pulling in the electron configuration and highlighting where that electron is removed from, both on the configuration and on the Bohr model shown. You might notice that the first electron to be removed is from the outermost shell of the atom. That makes it the easiest to remove since it's farthest from the nucleus and fairly weakly attracted to it. After that electron has been removed, my configuration is no longer 3s2. Now it's 3s1 and my atom has a +1 charge. When we remove that second electron from the 3s1, it's also coming from the outermost shell of the atom. That's why it takes a similar amount of energy to remove it, since it's also pretty far from the nucleus and also fairly weakly attracted to it. The slight increase is due to the fact that the atom now has a +1 charge. After that 3s1 electron has been removed, the atom now has a +2 charge and the electron configuration changes in a big way. So now to remove the third electron, it has to come from the 2p6 orbital. Or in other words, now it's coming from the second energy level. The second energy level means that it's closer to the nucleus, much more strongly attracted to that nucleus, and that's why it takes so much more energy to remove the third electron than it did the second. To summarize why that third ionization energy is so much higher than the rest, we can say that it was removed from an inner shell. That means it's closer to the nucleus, less shielded from the nucleus, and more attracted to it. Let's take a look at how this would work with a sodium atom. Here's its electron configuration and its 3 ionization energies. So sodium is a little bit different than magnesium. The second electron removal, that's where we see the extremely large increase. In fact, it's about 9 times as big as the first ionization energy, whereas the third electron removal only less than doubles when compared to the second. So for sodium, it's different because the sodium atom only has this one valence electron. So that first electron removal is pretty easy to remove because it's pretty far from the nucleus. Once that one electron is gone though, then we immediately start removing from the second energy level. So the second electron is removed from an inner shell. It's closer to the nucleus, less shielded from it, and more attracted to it. To really make the point, let's also look at aluminum's electron configuration and its first 3 ionization energies. In these values for aluminum, there is no large increase in ionization energy at all. And that's because aluminum has 3 valence electrons that are all fairly easy to remove. So for aluminum, we would remove all those 3 and not get to a very large increase until the 4th electron removal. That would have to come then from the 2p6. Aluminum's large increase in successive ionization energy wouldn't happen until the 4th electron removal. So here's all 3 examples we looked at with their large increase in successive ionization energy highlighted. Let's summarize by saying that it takes much more energy to remove inner shell or core electrons compared to valence electrons. That's because those inner shell electrons are closer to the nucleus, they experience less shielding, resulting in a stronger attraction to that nucleus and more energy needed for removal. These are the key ideas for the video, so make sure you take some time to write them down. That also concludes this video. Thanks a lot for watching, and here's a brief summary.